Hello, my name is Jonah Merwitz, and this is Physics 2211 Lab 3 Black Hole. Introduction. This lab is made up of two parts. Part 1, use code to analyze the motion of a star to determine the mass of a black hole. We got the average mass of the black hole to be 1.04 times 10 to the power of 23.4. Part 2, use the calculated mass of the black hole to determine the x and y components of the initial velocity of a spaceship so that it gets close to the black hole to orbit it but doesn't crash. Part 1, key concepts. We have F net equals F parallel plus F perpendicular, which is equal to the rate of change of momentum with respect to time, perpendicular component of that, plus the parallel component of that. And then below we have the definitions of the ways to find the perpendicular and parallel components of the net force, which is equal to the rate of change of momentum over time. Gravitational force, we have negative g m1 m2 over the magnitude of the radius between them squared times the unit vector pointing in that direction. And isolating it to find the mass of one of those objects, we have m2 equals dp dt, which is f net, times the magnitude of r squared over g m1. Part 1, glow script model. So in this section of the code, we just defined all of our variables. So we have g, mass of the star, and then delta t. That delta t is just the time of 1 day in seconds. And yeah, and then we have the on line 139, we have the updated time is the initial time plus delta t. So every 1 day, the time gets updated. Part 2 of part 1, glow script model continued. So in these ones, we just defined the initial momentum, final momentum, change in and initial velocity, final velocity, and then the changes in both of those by taking the final minus initial. dp dt, we define that as the change in momentum, delta p over delta t, change in time as defined before. F net is equal to dp dt, as I said on the second slide or third slide. And then the p hat, magnitude of the F net, and then the parallel components, we just define those with like norm, magnitude of the momentum, and then multiplying those two together. And then for F net parallel, we define that as dp dt parallel and dp dt perpendicular, because the F net equals the parallel plus the perpendicular component. We just subtracted the parallel component to find the perpendicular component. Part 1 results. We got the average mass of the black hole is 1.04 times 10 to the power of 34. We did that by just taking the average of all the masses that we obtained with the code. Part 2, the system, whichever mass we were looking at, and the surroundings were the other two masses in the system, in the surroundings. The initial conditions, the ship launches with an initial velocity that we kind of played around with and looked at the results to determine whether it would crash into the black hole or not. So basically all this code is that it calculates the net force on the moon and ship using the gravity equation, and it updates the ship's position and velocity every time step and repeats the loop to calculate many iterations. Part 2 results. We found that n ideal initial ship velocity was 2.44 times 10 to the 4 in both the x and y direction. So 2.44 times 10 to the 4, comma 2.44 times 10 to the 4 is 0. And the ship's trajectory was run and visualized, and these are the results we received, where the purple is the ship's trajectory. Possible sources of error. Other large mass objects would have an effect on the orbit of anything in space. The initial velocities in part 2 are a little off from ideal because it doesn't have the figure 8 orbit. And so the trial and error method was used to find the velocities, so it was obviously not going to be ideal. Discussion. What does it mean? The net force on the ship is determined by the gravitational attractions of both planets and the moon. The net force on the moon is determined mostly by the planet and a little bit by the ship because of its small mass, and vice versa for planet on the moon. The parallel component of the force to the direction of velocity influences the magnitude of momentum, but doesn't change the direction. And the perpendicular component is the opposite, where it changes the direction of velocity, but without changing the magnitude of the momentum, which leads to curving motion. What if, to predict the motion of the whole system, you need to calculate the force on the black hole, the planet and the black hole, plus what was already done before. Because of the black hole's mass, the interactions between the black hole and the planet will be very large. and the gravitational influence of the black hole on the planet will influence their stability in orbit, as well as with the ship. Conclusion: it is possible to utilize the gravitational equation to predict data about objects in space, and you can use this along with velocity and position update formulas to get better results over many different iterations. Thank you very much.